to show curl of magnetic field equals mu naught J plus mu naught epsilon naught del E by del T. So this is one of the Maxwell's equation in differential form. There are 4 Maxwell's equation in differential form. So this is magnetic field. Okay. And this is current density, which is produced by moving charges, and this is electric field. Okay. Now we know current carrying conductor produces magnetic field. So what does this equation mean? So this equation tells that in addition to current, magnetic field can be produced by varying electric field also. So we know current carrying conductor produces magnetic field. So in addition to current, which produces magnetic field, we can also produce magnetic field by varying electric field. Okay, so we find this. Now, in order to show this relation or equation, we use Ampere's law. Okay, so I'm writing from Ampere's law. Line integral of magnetic field throughout the closed path equals mu naught times the current inside the closed path. So let's call it equation 1. Clear? So we can understand in this way also. Suppose we have a current carrying conductor carrying current I in upward direction, and it produces magnetic field lines, okay, which is circular in nature. Now let us take a small length or elementary length, okay, dl in magnitude. On this closed path or loop, or this is also called contour C. Okay, so this is closed path, which is actually a magnetic field lines. And if we want to show the direction of magnetic field, then we have to draw tangent, okay, on this circular path. Okay, suppose if I want to assign the direction of magnetic field at this point, okay, then I have to draw tangent in order to show the direction of magnetic field. So the current I is steady, okay. So this current I is steady, and the closed path is enclosing steady current I. So we have this. Now, we use Stokes theorem, okay, on left hand side of equation 1. Let's say we have a vector. This is vector field. Then line integral of a vector throughout the closed path or loop. Okay. So this equals surface integral of curl of a vector throughout the closed surface. Clear? We can understand in this way. Let's say we have a closed path, okay, or closed loop. Let's say this is a counter or contour. Okay, this is a closed loop or closed path, and it is enclosing a surface, okay, S. And let's take a small elementary area, okay, ds on the surface. Clear? So we have this. So we have a closed loop which is enclosing surface S. Clear? Now let us replace A vector by magnetic field. Then we can rewrite this equation in this way, okay? So we have this. So we can replace this integral, okay, by this integral. Okay, so we need to note this, okay? So I'm writing applying Stokes theorem on left hand side of equation 1, okay? We can write in this way. Mu naught, and we have I, okay? Now, we know current I equals J dot area vector ds. And in integral form, we can write I equals this, okay? So we have this. So we can replace this current, okay, by this integral. So we can write in this way. Okay, so we have this. Now, let us take this term, okay, towards left hand side. So we get this, okay, on simplification. So we have this. Now, if this is not 0, okay, then the integrand, okay, curl of B minus mu naught J equals 0. So we can write curl of B equals mu naught J. So we have this. Let us call it equation 2. Okay, we have this. So I'm erasing this, okay? Now, taking divergence of equation 2 on both the sides. So we can write in this way. Here. So this equals. So we have this, and we know this is 0. Clear? So we have this. So we can write divergence. Okay, this is called divergence. So we can write in this way. 0, or we can write, since mu naught is constant, so we can write in this way, okay? So we are getting this. Let us call it equation 3. So we are getting this. Clear? Now, what does equation 3 indicate? We need to know that. So what we are getting? We are getting divergence of current density is 0. Clear? Now, we have this, okay? For curl of magnetic field equals mu naught J, that is current density, so for this, okay, for this to happens, J must be divergence less, because we have taken divergence of equation second, and finally we have obtained divergence J equals 0. And as we know, current density is produced by moving charges. Clear? So divergence J equals 0 only for steady current. Okay, this is 0 only for steady current flowing in closed path or closed loop. So we need to understand this. Okay, so I'm rewriting equation 3 over here. Okay, so we have this. So it indicates that there is no net outward flow, okay, of current, since the divergence of current density is 0. So it means that current has no source or sources or sink. So what does it mean? So what does this statement mean? That is, current, okay, do not have starting or stopping. stopping point in a circuit. So we need to understand this. That is, there is no start or no stop of current in a circuit. So this means that current must flow continuous in the entire circuit. Entire circuit. So we need to understand this. Clear? Now, divergence J equals 0 is valid only for steady current. Clear? So if you consider this, let's say you have a RC circuit, okay? This is R, and you have a capacitor, okay? Connected in this way. Let's say you have a RC circuit. So we have this. So I'm not using key, okay? Now what do we find? Conventional current, okay, is flowing along this direction. That is from positive terminal to, okay, positive terminal towards the upper plate. Clear? So we find conventional current which represents the flow of positive charge. Okay. So positive charge is flowing from positive terminal of battery towards the upper plate. Clear? And we find there is a gap between the plates of the capacitor. So charge do not flow or do not cross from one plate to another plate of the capacitor. And as I said earlier, conventional current which represent flow of positive charge, okay, and positive charge can be considered to be flowing from positive of the battery, that is positive plate of the battery, to the upper plate. And in addition to positive charge, electron, okay, flow from negative plate or terminal of the battery towards the lower plate of the capacitor. And if electron is flowing along this direction, then we can assume equal amount of positive charge, okay, is flowing from the lower plate towards the negative terminal of the battery. So what we are finding is that conventional current is flowing from positive towards the upper plate, okay, and it is flowing from lower plate towards the negative plate of the battery. And there is a gap between the plates of the capacitor. So we need to understand this. So there is no charge, okay? There is no charge flowing between the plates, of the capacitor. But what we find is that even though there is no charge flowing between the plates of the capacitor, there is magnetic field between the plates of the capacitor. So you need to note this, okay? So there is no charge flowing between the plates of the capacitor, but still what we get, magnetic field between the plates of the capacitor. So we can think this in this way, okay? Current starts and stops on the capacitor plate, okay? So we are having this. So what we are getting divergence of J equals 0. Clear? But what we are finding, current has to flow continuous, okay, in the entire circuit. So current has to start and stop. So current has to stop and start on the plates of the capacitor. Therefore, current density must have divergence or must be diverse. So we must have divergence of J, because we have current which must flow in the entire circuit. Okay. So we must have divergence of J. We cannot have divergence of J equals 0. So this contradicts. So this relation contradicts. Okay. This contradicts. So we cannot have this. Okay. So we need to understand this. So I'm erasing this. Okay. Therefore, what we do is that, or what Maxwell did, okay? So we have this, because Ampere's law is valid only for steady current. And if we have steady current, then we get divergence of current density equals 0. But we find magnetic field between the plates of the capacitor, and we cannot have divergence of current density equals 0. Clear? So for that reason, Ampere's law has to be modified, and Maxwell modified Ampere's law. Okay. So he introduced J dash, okay, which is current density. Clear? This is current density, because we are adding J dash with J. Now let's take both sides. So we can write in this way. And we know this is 0. So we can write, okay, so we have this. So we can write so finally we get divergence of J dash, okay, equals divergence J, okay? Divergence J dash equals divergence J. So we have this. And we know equation of continuity, clear? So divergence J plus d rho by dt equals 0. And rho is called charge density, or it is volume charge density, okay? So from this equation, we can write divergence, okay, J equals minus del rho by del T. So we have this. So we have negative sign in this equation, okay? So divergence J dash equals minus del rho by del T. So we can write in this way, okay? So we have this. Okay, so we have this. Now I'm erasing this, okay? So I'm taking this equation. So we have this. Now we know divergence of electric field, okay, equals rho by epsilon naught. This is one of the Maxwell's equation in differential form. So in this relation, we have divergence of current density J dash, okay? So we can write in this way, okay? This relation. Epsilon naught is constant, so we can write in this way. So we have this. So I can put this in bracket also. And we know epsilon naught E equals D vector. And this is called electric flux density, okay? Or displacement vector. Clear? So we can write now let's put rho equals this. Okay, so we have this. Now after doing simplification, we can write so we have this, and from this relation, okay, we can write current density J dash equals del by del T epsilon naught E. So we can take epsilon naught, okay, outside. Since it is constant, so we can write this. Clear? So we can write current density J dash equals epsilon naught dE by dt. Clear? So we have this. So let's call it, this is equation, or let's put, okay. Let me write in this way. Putting J dash equals epsilon naught del E by del T in equation 3. So we get curl of magnetic field equals mu naught current density J plus current density J dash, and J dash is epsilon naught del E by del T. So we can simply write in this way, okay. So we have this. Clear? And if you look into this expression, okay, we can also rewrite in this form. Current density J dash equals del by del T, and epsilon naught E is D vector. So we have this.